All right. So last time, what we did was we started kind of looking at systems of equations, how to solve them, how to get solutions. And what we did, the most efficient way to do this is put this into a matrix. And so we're going to talk a little bit about that technique and how to manipulate it. So a leading entry of a row, let's see, a non-zero row matrix is the leftmost non-zero entry. So for example, if I give you this matrix here, and I say, okay, what are the leading entries? This row has none because all the entries are zero. The leading entry of this one is this, and the leading entry of this is this. It's just the leftmost non-zero entry in any row of the matrix, right? Definition. So a rectangular matrix A is in echelon form, or sometimes row echelon form, if following through are true. Okay, so what does it mean for a matrix to be in row echelon form? Number one, all rows of only zeros are at the bottom. Okay, so right out of the gate, this one right here is not in row echelon form because the zero row would need to be on the bottom. Right? The leading entry entry of any non-zero row is to the right of the leading entry of the row above. So by the way, as I put this definition up, let's try to cure this matrix right here. This isn't in row echelon form because the row of zeros is at the top, right? Well, one of the things that we talked about last time is we like to be able to manipulate. We like to be able to manipulate the rows however we want. So let me fix this. I can swap any row, so I'll do that. Well, now I've got the first condition. My row of zeros at the bottom. But now it doesn't satisfy the second one because to be in echelon form, the leading entry of any non-zero row must be to the right of the leading entry of the row above it. So notice this is the leading entry here, and it's to the left of the leading entry of the one above it. How can I fix this?
Swap the bottom or top of the middle row.
Do another swap. That's right. And finally, the entries in any column below a leading entry are zero. Uh, below. Do I have further problems with matrix I have? I think this one's now good to go, right? Because I've got zeros below every leading entry. I agree with it. So this animal right here, yay, is in echelon form. Right? But we actually want to do a little better. So I'm going to add a couple other conditions. So additionally, so that's row echelon form. Now I'm going to give it some steroids here or something. If the next two are satisfied, then the matrix is in row reduced echelon form. Row echelon. So we've got to have these first conditions plus these other two. 4, all leading entries are 1. Not rows. One and 2. Each leading entry is the only non-zero entry in its column. Okay. This one is in echelon form, but it fails both of those last two, right? Because this leading entry isn't 1, and this leading entry doesn't have all zeros in the column except for 1. But again, we can fix that. What other row operations can we do to further adjust this one? I want that to be a 1, right?
Divided by 2.
How about that? I can multiply the top row by 1/2. 1/2 is not 0, so I can do that. Whoops. All right. Now I'm almost there because all my leading entries are now 1. But I've got to have all the other entries in the column of every leading entry have to be 0. I'm good to go here. What about this one? How can I fix that?
Subtract the first row by the second row twice.
Right, so I can just use this 1 to take out that 2. Let's multiply this by -2 and add up here. And I get 0, 1, 0, 0, 0, 1, 0, 0, 0. That is row reduced echelon form for the original matrix that I put up there. Now, here's kind of the cool thing about it, because there are many ways you could have done things a different order than I did, taken a different approach or whatever. But here is kind of a big theorem. Every matrix A reduces to a unique row reduced echelon form. echelon form is not unique necessarily. Two different people might get two answers. But if I give every one of you a 25 by 30 matrix filled up with numbers, right? And I say, okay, reduce this to echelon form, or I'm sorry, row reduced echelon form. You all might take all kinds of different approaches, different ways. You might do things in different orders, but you will all get the same answer if you do it right. That's what this theorem says. Start with a matrix A, you reduce it to row reduced echelon form, everybody's going to get the same answer. And in mathematics, that's often quite important because it would probably be kind of a mess if you got different answers, right? Because then, you know, the problems may come out differently. I need to give you another definition here. And then we're going to start doing some lots of examples. Okay. Definition. How many of you have ever heard the word pivot? I mean, not in the English language, but in the matrix sense. Anybody ever heard that before? Okay, good. Well, don't ever say I never gave you anything. A pivot position is the position of the leading entry in a given row. A pivot column is the column of pivot position. Okay, so I'm gonna take this apart. Let's start with kind of with this example here. Suppose I give you this matrix here. 1, 2, 1, 3. Minus 1, 2, 4, minus 1, and minus 1, 2. Now, what are the pivot positions? I don't know yet. I don't know, but I will after I reduce it down. Now, notice I am going to reduce this. Let's reduce this down to row reduced echelon form, and we'll take apart what the pivots are and so forth. Notice there's many ways to do this. You could key on this -1 or this 1. You might do it a different way than me, but again, the previous theorem says that no matter how you go about this, once you're done, you should get the same answer. I am going to use this first row. So next step, I'm going to have that. I'm going to take out this, multiply by -2. Take that out. That's going to give me 0, 0, 2, -7. Everybody agree with that? You better watch me at this hour of the morning. Man. And I'm going to use it to take out this one just by adding it. So I'm going to get 0, 4, 1, 6. By the way, can anybody? So what I'm going to systematically. Can anybody tell me what one pivot position is? Any of them? Yeah.
So it would be the 2 in the second row. So what is that? Third column.
Yeah.
Second row.
You started off with a hard one, yeah. This is a pivot position,
yeah,
I'm sure, right? But he's right. This one will be, and this one will be too, and we'll see how this kind of carries out. I want to go. It's got to kind of go slant down like this because remember, you have to, as you go up the matrix, you have to be moving this way with regard to your non-zero entries. 0, 0, 0, 4, 0.160027. That looks right to me. Now, at this point, I'm gonna bite the bullet. So here, it looks to me like I've got that, that's right there, what I've got is echelon form. Everybody agree with that? Yes.
You dropped the negative from seven.
Did I? Thank you, thank you. I wanna do that. But does everybody agree I've got it in echelon form, right? Next thing I'm gonna do is I'm gonna turn these animals into one so I can satisfy that. So let's do that. 1, 2, -1, 3. And 0, 1, 1/4, 3/2. And I'll divide by 2 here. Right. And now I can use those ones to sweep things out. It's actually easier. If you follow the textbook, your textbook says, "Oh, start this way and work towards your left," which you don't have to do it that way, but it is easier, right? So I'm going to use this one to take these guys out up here. Am I okay with that? So I'm going to multiply this by what? -1/4. So in the next step, 0, 0, 1 minus 7/2 is going to be left alone. I'm going to multiply this by -1/4. That's going to take that out. That's kind of the whole point. When I multiply that by -1/4, I get 7/8, and that's going to be 12/8. So I'm going to get like 19/8. And then to take this out, I'm just going to straight up add it. And that's going to be 1, 2, 0, and that's going to be -1/2. Okay, then. And what's the final thing that I need to do? Okay. The last thing I need to do is I need to take this out right here. So 0, 0, 1 minus 7/2. 0, 1, 0, 19/8. And let's see, to take this out, I need to multiply that by negative. All right. So that's going to give me 1, 0, 0. So it's going to be -19/4 minus 2/4 is -21/4. And now this is in row reduced echelon, right? The ones go down to the right, and right, I've got and every leading entry only has it's the only entry in the column. Everybody see how to do that? These are the pivots, and the columns they're in are the pivot columns. Everybody clear on that? Okay. All right, so we're going to use this on systems, and you might wonder how this is silly manipulation and how does this help? Well, I'm going to start off with kind of a very basic example. Uh, Let me start off with a simple system. Uh, How many solutions does that have? It's got infinitely many. Isn't this just a line? Right? So this has actually got infinitely many points to satisfy, right? And remember, I could plug in anything for x2, and that's going to tell me what x1 is, right? If I plug in 0 here, then x1 is 4. If I plug in 1 here, then x1 is 6. So, agree with that? If I wrote this as a matrix, well, I feel a little silly, but I'm going to do it anyway. My augmented matrix might be 1, -2, 4. How do we find the row reduced echelon form of that? Y'all looking at me like I'm an idiot because I'm being an idiot. It's only got one row, right? And look at me, the leading coefficient or the leading entry of my one non-zero row is 1. I've got no columns problems, do I? So this is already in row reduced echelon. Everybody agree with that? Already go. If this had been a 3, I'd have to divide out by it, but I'm already good. How many pivots do I have? 1. There it is. Okay. So let me kind of think about this way. So kind of the common sense approach to this, any solution is of form x2. And what x2, I can rewrite this equation this way. Everybody agree with that? X1 is 2x2 plus 4. So any solution of this thing is the form x2 and x1 should be 2x2 plus 4. This completely describes the solutions of the system, right? For example, when x2 is 0, then x1 has to be 4. When x2 is 1, then x1 has to be 6. When x2 is -2, then x1 has to be 0, right? This parameterizes all solutions, right? Right, agree with that? So I can let x2 be anything I want, and that controls what x1 is, right? Each pivot column, and there's only one here, is a basic variable. Well, let me say, I should say is, corresponds to. And the others correspond to 3. And I think free is a suggestive terminology. Because what it means is when it's a free variable, it means you can plug in anything you want for it willy-nilly. Basic means the frees tell, basics are determined by what the frees do. So in this example here, x2 is free. I can let x2 be anything under the sun I want. And then that tells me what x1 is, right? So the frees are the ones where you can do anything you want, and the basics are the ones that are determined by what happens to the free ones, or what you choose for the free ones. Let me give a slightly bigger example with frees and the basics here. And then we'll do it a bigger. The next example, let's look at this. What if I give you this? X1 plus x2 plus x3 is 1, and x2 minus x3 is equal to 4. Okay, let's dress this up in an augmented matrix and see what we can do. 1, 1, 1, 1, 0, 1, -1, 4. Okay, everybody good with how I got the augmented matrix here? Okay, what do I want to do now? I start off on my quest to get this into row reduced echelon form. And then I'll show you how to pull it out with the basic phrase. This is already good because I've got lots of ones here, right? In fact, this already looks like it's an echelon form, right? It's just not row reduced. I agree with it. So let's go for the row reduce. Use this to take this out. Multiply this by -1 and add it to the top. And I get 1, 0, 2, -3. That look right to you? Okay. So what does this mean? How many pivots I got? I got 2. These are the pivots. So this means x1 and x2 are basic. They correspond to pivot columns. I've got one column, not counting the one on the other side of the dash. I got one column here that is not a pivot column. That's my free variable. Everybody okay with that?
Yes. One more time, what you said? What's it called?
This is the non-pivot column.
Okay.
So here I've got one in exactly one non-pivot column, and all the non-pivot columns, I did write that down. Okay, right. The others, the non-pivot columns correspond to free variables.
Okay. Gotcha.
And this row reduced echelon form helps us back substitute to our solutions. Let's rewrite these now that I've simplified this a little bit. The first equation corresponds to x1 plus 2x3 is equal to -3. And the second equation is x2 minus x3 is equal to 4. Agree? And think about what's going on here. Remember, I said that x3 is our free variable. So x3 is the one that I can plug anything in that I want for it. And notice how that determines x1 and x3. All right. So in other words, let me rewrite the basics in terms of the frees. x1 is equal to -2x3 minus 3. And x2, the second basic, is x3 plus 4. How many of you have ever used vector notation? You probably have if you've been in Calc 2, maybe you might have talked a little bit about it, or if you've been in physics or dynamics class or whatever. We're going to talk about that a little bit. So here's my solution. x3 is free. And when I say that, I mean I can pick it to be anything I want, whatever number you want to plug in. And once that choice is made, the next one is -2x3 minus 3. The choice of x3 helps me here. And x2 is x3 plus 4. And so I might write the solution this way. So we'll get used to this notation. Well, x3 is free, so it just is what it is. This is x3 plus 4. And this is whatever x1 was. Where are you, x1? There, -2, x3 minus 3. So you can use this formula here to churn out every possible solution, right? For example, you can let x3 be 0. One solution to this set of equations is -3, 4, 0. So if you put in -3, 4, and 0, you should balance both of these equations. You could put in x3 equals 2, giving you -7, 6, and 2. That should be a solution. And every solution is bought out using this formula. x1, x2, x3. Everybody okay with that? Okay, let's do one that's got even a little bit more juice to it. How about this one? How about X1 plus X2 plus 3X3 plus 4X4 is 3. X1 plus 3X3 plus 5X3 plus 2X4 plus 2X5 is equal to 5. And X1 plus 2X2 plus 4X3 plus 3X4 plus 2X5 is also equal to 5. Good, good. Okay. Let's take this one. First thing, right? This is a matrix. One, 1, 3, 4, 1, 5. Oh, I messed up. 3, 1, 3, 5, 2, 2. 5. And 1, 2, 4, 3, 2. 5. Okay. So, when you look at this original equation, it's not really clear if there's a solution or what a solution is it? Right? We're going to make this, because we've got 3 equations, 5 variables. It's not clear at all to me what the solutions, if any. It might be inconsistent. So I'm just going to be simple-minded. 1, 1, 3, 4, 1, 5. I'm just going to multiply this by -1 and add, multiply by -1 and add, like that. So it's going to give me 0, 2, 2, -2, 1, 2. Right, times -1 and add. Yes.
I think you swapped the 3 for a 5 in the
Where did I do that?
in like the am I wrong or in the top right corner of the matrix? In the second one it's a 5.
Oh, so I did. Thank you. Multiply this by -1 and add it here. I'm going to get 0, 1, 1, -1. 1, 2, I guess. Anybody see what perhaps I should do at this juncture?
Try to change your 2 on the second row to a 1.
Yeah, I can do that, but I'm a lazy, lazy creature. And one thing that I do see is this middle guy is like almost like -2 times this, right? Or 2 times this. So this might be a little shorter, I hope. I'm gonna leave this top one alone again. So I'm gonna multiply this by -2 and add it to this. And that's gonna give me, so I'm still gonna have 0, 1, 1, minus 1, 1, 2 on the bottom. And when I do that, times minus 2 and add, I'm gonna get 0, 0, 0, 0. Minus 1. And that's going to be minus 2. That looked right, yeah. Oh, now I've got ones everywhere. I'm loving it. And just to make this, I'm gonna do this. Let it do that. Change the sign of that one. Okay, let's do a step of. Let me rearrange here. I'm gonna go now. 1, 1, 3, 4, 1. 0, 1, 1, minus 1, 1, 2. So I move the middle row in the middle, and I'm gonna take the middle row from over there, put it on the bottom. Now, to make this row reduced echelon form, I'm going to use just 1 to take out everything above it. So times minus 1 and times minus 1 and add in both cases. So my new matrix should look like 0, 0, 0, 0, 1, 2. When I multiply this by minus 1 and add it up here, it kills both these things here. And I get 0, 1, 1, minus 1, 0, 0. And I'm going to kill this. We'll get 1, 1, 3, 4, 0. Okay, so far. And I guess the last, if I really want row reduced echelon form, I need to use this to take out this one here. And that does, it's not just busy work, it does make my life simpler. We'll see how this fleshes out in a moment. This is 0, 0, 0, 0, 1, 2. This is 0, 1, 1, minus 1, 0, 0. And when I multiply this by minus 1 and add, I'm going to get 1, 0, 2, 5, 0, 1. This matrix, how many pivots do I have? This is now in row reduced echelon form, right? How many pivots? 3. Agreed. I've got 3 pivots. And so what that matrix is, they're the voices again, and it's telling me that these 3, x1, x2, and x5 from the pivots, they're my basic variables. And the basic variables are determined by the free variables. Which ones are the free?
The other one.
Like the ones from the non-pivot columns. And so, let me write down these simpler equations that I have. The first one is x1 plus 2x3 plus 5x4 is equal to 1. The next one is x3, I'm sorry, it's x2 plus x3 minus x4 is equal to 0. And what's the last equation?
So it's equal to 2.
That's right. It's determined by the free variables in a very silly way. And no matter what, every solution has the property that x5, no matter what, x5 has to be 2, right? There's no variance in that. But there are infinitely many solutions, right? And notice I can rewrite these equations this way. Minus 2x3 minus 5x4 plus 1. And x2 is equal to minus x3 plus x4. And so see, my basics, x5, x1, and x2 are determined by the free variables. Here's a formula of free variables, here's a formula, and this is trivially a formula of free variables. What do the solutions to this look like? Let's write down the solutions. Solutions look like x5 is 2, no matter what. X x3 and x4 are basic. I'm sorry, x3 and x4 are free. So they just are, you can pick x3 and x4 any two different ways that you like. X2 is plus x4, and x1 is minus 2 x3 minus 5 x4, and then tack on 1. These are the solutions. Pick any two x3 and x4 that you want. X3 equals 1, x4 equals 2, and that will give you a solution. So if you do that, 1 and 2, then you get minus 11, 1, 1, 2, 1. That should be a solution. And this parameterizes all. You've got 2 degrees of freedom now, right? Because you can pick x3 and x4 independently of each other. Okay, any questions on that? Okay, one question that might be bothering a little bit is with every example that I've done here, I always got a solution, right? What happens if I have something like this? Let's try this. Let's say, try this one here. What I've shown you basically is a nice way for writing, and this is, we're going to talk about writing this notation. I call this a vector notation for your solutions. What happens if you get something like this? Let's look at this system really quickly. I'll write the matrix for this. I get 1, 1, 1, 1. And I have 1, 1 minus 1, 4. And then I get 2, 2, 0, negative 1. Well, let's go about our business and try to see what we can get. I'll use this. I'm going to leave the top row the same, but I'm going to use this 1 to take things out as I'm accustomed to. Multiply this by negative 1.5. I get 0, 0, minus 2, 3. and multiply this by -2. And add, and we'll get 0, 0, 2. Well, it's -2. That should be -2, shouldn't it? 0, 0, -2, and -3. Okay with it? Plus 0, 0, 1, minus 3 halves. I'm going to divide by -2 here, divide by -2 here. And now I'll use this to take this out. 1, 1, 1, 1. I'm not even going to go all the way to the row reduced echelon form. 0, 0, 1, minus 3 halves. Multiplies by -1, and I get 0, 0, 0, 3. Can somebody interpret that last row of the matrix? Yeah, that's right. This last one right here is 0x plus 0y, 0 z equals 3. But this is has to be 0. This is inconsistent. And in fact, this always works. Let me make that more precise. There. A system is consistent if and only if the row reduced echelon form of its augmented matrix has no row of form 0, 0, 0, B. You not see. So if you get any row that has all zeros on the divider side and something that's not 0 on the other side, it's inconsistent. And that's an if and only if. That completely determines it. If consistent, if it's consistent, then solution is unique if and only if no free variables. So in other words, here, let me break it down for you. If you ever get a row that looks like this, it's inconsistent. Throw it out, no solution. If you don't get a row like this, then it's either got free variables or it doesn't. If there are no free variables, that is, if every one of the columns on this side of the thing is a pivot column, then there's a unique solution. There's one and only one solution. On the other hand, if there's at least one free variable, then there's infinitely many solutions. And we've shown how to parameterize. Any questions on that? Yes.
I'm just curious how you went from that on one perspective
From here to
from there.
from here to here, I'm multiplying this by -1 and add it down here. Other questions? All right. Well, the first quiz I'll probably post either today or over the weekend. Other than that, y'all have a good weekend and we'll see you on Monday.